Hi, this is Dane Quinn from the University of Akron, and this time we'll do an example dealing with projectile motion. Here's the problem. A particle of mass m here is launched with an initial inclination theta, so that's the angle at which the initial velocity is located, while a cart, represented here, moves with constant velocity, u in the I direction, and is initially located some distance d from the particle. So the question is to find the initial speed of the mass, so the magnitude of the velocity, so that it lands, as it travels along this path, into the cart. And then, after I found that, I'd like to ask how far, ultimately, is the ball thrown. So here, again, this is a problem in projectile motion. So only the gravitational force acts on the particle. We are neglecting everything else, such as air drag or any kind of other effects. And we assume planar motion. So the path of the particle is in the plane. So now with that, we would like to define coordinates and directions that will help us to describe the configuration of the system, including the position of the ball and ultimately the position of the cart as well. So in terms of coordinates and directions, let's start off with I and j being horizontal and vertical directions relative to the ground. Then, if I look at the position of this particle, right, so let's define a position vector as r of b with respect to O. Then, using Cartesian coordinates, we will identify the component in the I direction as measured by the coordinate x, and in the j direction we will measure the displacement as y. So again, both x and y are coordinates, right, so they're functions of time, as is the position vector, b with respect to O. So now, in terms of these coordinates, we can write the position vector as r of b with respect to O is x in the I direction plus y in the j direction. And this describes the displacement of the ball. Here x and y are measured from the initial position of the ball. So now looking at the cart, we'll do a similar procedure. Again, we have defined I and j as directions horizontal and vertical. Then the position of the cart, right, if the cart is described by a point C, the position of the cart is c with respect to O, and again a function of time. And we will measure the displacement of the cart in the I direction as W. As a result, the position of the cart, or the position of the point C, can be written as r of c with respect to O is equal to W, that measured coordinate, in the I direction. Now, if I recall the problem statement, the cart moves with constant velocity. Vc is equal to ui. And now, in terms of this coordinate that we've measured, the velocity of the cart is w dot in the I direction. So again, the derivative of w with respect to time. From the problem statement, this is u in the I direction. So here we have written the velocity in terms of the coordinate, and then we've expressed that in terms of the constant value, the constant speed that was given in terms of the problem statement. And as a result, we have w dot is equal to u. So I'm going to integrate this to find the actual displacement w. So to integrate this, I'll introduce a dummy variable, tau, in my integration. So I'll take this, w dot is equal to u, and I'll integrate it from 0 to t. And again, tau is the dummy variable. So when I do this, carrying through this integration, we have w of t minus w at time 0. Again, this is the integral of a derivative. So it's the argument, w, evaluated at the endpoints, equals u of t. Now, recall from the problem statement, once again, the cart was initially located at distance d from the origin, which means that w at time 0 is equal to d. And we can then solve for the displacement of the cart as u of times t plus that initial displacement d. So here we have a description of the motion of the cart. Now, turning back to the particle, the equations of motion arose from linear momentum balance, and we've done this in a separate video lecture, so I won't repeat the derivation, but I will start off with the acceleration. So from linear momentum balance, we had x double dot was equal to 0, and y double dot was equal to minus g. Here, the initial velocity was expressed in terms of speed and direction. So the initial velocity of b, the ball, we can write as a component in the I direction plus a component in the j direction, and that would be vx and vy. Then in terms of the speed and inclination, that becomes v naught, the speed, and then we have the direction, which is cosine of theta in the I direction plus sine of theta in the j direction. So this represents the initial direction of the velocity. So now comparing components in the I and j direction, we find that vx is v naught cosine of theta, vy is equal to v naught sine of theta. Since we're measuring from the origin, the initial displacement of the ball in the I direction was equal to 0, and the initial displacement of the ball in the j direction was equal to 0. As a result, the equations of motion, when integrated twice, give me the velocity and position of the ball. So x dot, as a function of time, is simply v naught cosine, while x, as a function of time, v naught cosine theta times t. Likewise, y dot, as a function of time, is minus g times t plus v naught sine theta. And finally, y of t is minus g over 2 t squared plus v naught sine theta times t. So at this point, we have the displacement of the cart as a function of time, and we have the displacement of the ball in both the horizontal and vertical directions as a function of time. In addition, we also recover the velocity of the ball as a function of time. Now that we have the motion, we need to identify when the ball lands in the cart. So essentially, that occurs at some time, which we'll identify as t equals t final. So at this time, really, the ball and the cart are at the same place at the same time. Right, so let's go back and look at that initial figure. Right? Initially, the ball is over here, the cart's here, the ball moves up and then back down, the cart moves over, and we see that at this final time, the position of the ball is identical to the position of the cart. So at that specific instant in time, t equals t final, the ball lands in the cart. Or, mathematically speaking, the position of the ball with respect to the origin, again at t equals t final, is identical to the position of the cart with respect to the origin at this final time. Right, so again, they're in the same position at the same time. So in terms of the coordinates that we've measured, the position of the ball was x, and again, we're evaluating at this final time, plus y, evaluated at the final time in the j direction, is equal to w at the final time in the I direction. So this is a vector equation, and from this we can generate two scalar equations that will allow us to solve for the initial speed, which is what the problem requested. Along with that, we'll also identify the final time at which the two are coincident. So in the I direction, we have x of t final is equal to w of t final. Looking now at the motion for the ball, so let's go back here, x at t final is this expression evaluated at the final time. So x t final is equal to v naught, and I'm going to draw that in green because that's the unknown. That's the thing that we're looking for. V naught cosine of theta, and then I'm going to represent the final time in blue. That's also unknown. The position of the cart is d plus u times t final. Again, we're representing the final time in blue. So in blue and green, we see our two unknowns. That's one equation, and the other comes from the component in the j direction, which reduces to y of t final equals 0. Notice that there's no component in the j direction, but we could just as easily write 0 in the j direction. So y t final is equal to 0. Again, looking back at the equations for the motion, this is minus g over 2 times t final squared plus v naught sine of theta times t final, which equals 0. So here we have two equations, right? One here and one over here, that we can solve for our two unknowns, namely the initial speed, v naught, and the time required for this to occur. So from this, we will solve for t final. Now, from this second equation, I can rewrite this as t final, which I'll factor out, and then minus g over 2 times t final plus v naught sine of theta. And we see two solutions. One solution is t final equals 0. Now, this equation comes from the displacement in the vertical direction. So if I look back at the original problem, initially, both the ball and the cart have 0 vertical displacement. So t equals 0 implies that y at 0 equals the vertical displacement of the cart. So this is a solution. It's not the solution we're interested in, right? But it is a solution. The solution we're interested in comes from this second piece, and that can be solved so that t final equals 2 sine of theta divided by g times v naught. So if I know v naught, I can solve for t final. But of course I don't yet, so I will take this, introduce it back into this equation, and find the following. V naught cosine of theta minus u. So I've taken this term, moved it to the left-hand side, and I've factored out the t final. But, of course, t final is 2 sine of theta over g times v naught equals d. So, we need to solve this equation. Well, this is quadratic. Notice we have a quadratic term in v naught. We have a term that's linear in v naught, and then we have a term that doesn't depend on v naught. So I can write this equation in the following way. 2 sine of theta cosine of theta divided by g times v naught squared minus 2u sine of theta divided by g times v naught minus d equals 0. So again, here we have a quadratic equation. So this can be solved, right? And now, in doing so, we use the quadratic formula, and I'm going to go ahead and solve this and write down the answer. Here I've done a little bit of manipulation, but in doing so, we solve so that v naught is equal to u over 2 cosine of theta plus or minus now the square root of u over 2 cosine of theta squared plus d times g divided by 2 sine theta times cosine of theta. So again, if you take the quadratic equation and you solve this, you can reduce it down to this form. Or, in particular, this is u divided by 2 cosine of theta. So I'm going to factor this term out of everything. And we have 1 plus or minus the square root of 1 plus now 2 dg times cosine of theta divided by u squared sine of theta. So I realize this is a lot of algebra, right? But perhaps you can pause the video lecture, video solution at this point, and work through and come to this form. If you have a hard time with that, maybe just pick some numerical values and make sure that the expression that I have when you choose some numerical values matches the expression that you find when you choose the same numerical values. Right. So here, notice that this quadratic equation and the expression for v has two solutions, right? Because we have 1 plus this square root, and then we have 1 minus this square root inside these brackets. So note, there are two solutions. But only one of them is positive. If I go back and look, this term under the square root is greater than 1, right? Because I have 1 plus something. So again, this square root is greater than 1. Well, I have 1 plus something greater than 1, and then 1 minus something greater than 1. So the negative solution here is actually going to be negative. It will be a negative velocity. So that's not the solution we're interested in. We're interested in the solution that's positive, or the positive branch of the solution. So the solution that we choose here is v naught is equal to u divided by 2 cosine 1 plus square root of 1 plus 2 dg cosine of theta and u squared sine of theta. So we found the velocity that leads to the ball landing in the cart. So now we can go back and solve for the time. The final time we found was equal to 2 v0 sine of theta divided by g. So really taking this expression for v0, putting it into here, we can write this, and notice that the 2's will cancel out here. We actually have a sine theta divided by cosine of theta, so that's going to be tangent. So we'll write this as u times tangent of theta divided by g times 1 plus square root 1 plus 2 dg cosine of theta u squared sine of theta. So this is the final time at which the ball lands in the cart. And finally, we asked for the distance. That's going to be x final, which is x at t final, which is also equal to w at t final. And so to calculate this, I'll actually use the expression for w. Turns out it's a little bit easier, right? Because that was, let's remind ourselves, w is ut plus d. So the final time is equal to d plus u times t final. So that finally results in u squared tangent of theta divided by g 1 plus square root 1 plus 2dg, and then all the rest of these terms. So notice that here there's a good bit of algebra that I have kept. And if you want to work this problem out using some numerical values, that's fine. One of the advantages of keeping variables into any problem that you solve is that now I'm able to explore what happens as I change, say, the velocity of the cart. Right? How does that affect the solution? Or the angle of inclination, right? Or the distance that the cart starts. Right, so now I have a general expression that I can use for any number of possible scenarios. So to finish up, I'd actually like to kind of go and graphically represent what's going on. So I'm going to plot the position of the cart, I'm going to plot the position of the ball, and I'm going to kind of show in this three-dimensional plot how they intersect. So I'll start this with the motion of the cart. So the cart starts a distance d. And again, here x is in this direction, t is sort of back into the plane. So if I look at the motion of the cart, the trajectory of the cart, right, in the xt plane, it will start here at x equals d, at t equals 0, and it will increase linearly in time, right, and it will come to here. So maybe this is the final time that we find. So looking at this, this would be the final time, and this would be the final value of x. And of course the final value of y is equal to 0. So this is the motion of the cart. Now I can go and look at the motion of the ball. So the ball here, I'll do that in gray in terms of x versus t and y versus t. So again, x versus t, the ball actually moves on a straight line, right? Because again, x increases linearly in time, right? So that projection might follow a path such as this, while the vertical displacement as a function of time, right, is actually going to be parabolic, right? So that projection might look something like this. So again, we have the vertical motion and the horizontal motion of the ball as a function of time. Here in blue we have the trajectory, the motion of the cart as a function of time. Right, so all I need to do now is to take these two and express them in three-dimensional space. Right, so maybe the ball actually follows some path like this. And again, here I've tried to draw this in space-time. So x is this direction, y is this direction, and t is back into the board. So here, again, I've tried to kind of geometrically represent the path that the ball in green might take versus the path that the cart would take in space. And we see that they start off at different places, right, at time t equals 0, and then at the final time, right, they actually meet. So the final position of the ball is the same as the final position of the cart. So this is a good example with projectile motion and sort of non-trivial auxiliary conditions, right? So we've required that the ball land in the cart, right? And we've given conditions on the cart, and ultimately we've solved for the initial speed required to make that happen. Again, this is a fairly complex example with projectile motion, right? But it really covers a lot of different things. So that's it for this example. Thank you, and I will talk to you again.